Hey everybody, so we're going to try to do a little lesson here on projectile motion. This is stuff that we did before, but it's definitely been a little while since we've done this, so I figured putting together a little review video would not be a bad idea. Not sure how this will work with my little camera on here, but we'll see how it goes. There's my cat. Hi cat. Always. So anyway, projectile motion. Projectile motion is that idea of launching something up in the air and then watching it kind of fly through space. Remember that the key idea with analyzing projectile motion is to think about it rather than as a complicated curve, to think about it as the combination of two different simpler types of motion, which is horizontal motion and vertical motion. A cat. With this, the two key things to keep in mind of on this is that with the horizontal and vertical motion, we've got two kind of different sets of rules that govern horizontal and vertical. So for you guys, the hardest thing for students to do is to kind of remember we've got these X's and Y's that you got to really kind of keep them separated in terms of what you're doing with them. So the first thing, the easier half of it, is to think about the horizontal component, which is the X component, just how far out it's going. With horizontal motion, we're going to make the assumption that it's simply going one speed, that it is not accelerating, that it's literally just being governed by inertia, and it's going consistent speed to it. So you can kind of see up here, up on the screen, big idea up here is that we've got, number one, constant velocity. That's the key thing that you can get, is that horizontally, initial velocity and final velocity in the X direction are the same. That's a big thing. And because they're the same, we can use this equation that's down here, which is velocity is distance divided by time. Since it's not accelerating, we can do that. So Vx, or horizontal velocity, is dx, horizontal distance, divided by time. Remember that dx is the range, or it's the distance that's on the ground. Okay, vertically is a little bit more complicated, because with vertical motion, of course, now we're talking about more of a situation with free fall that's happening. So we've got to use acceleration due to gravity, and this is the y components of what we're doing on here. So with these, again, you're talking about horizontal and vertical. This case, the vertical motion is acceleration due to gravity, free fall. It can act just like you're dropping it off of a cliff, and all the same stuff that we did back in chapter 3 or whatever that is, are all still the same. So for this, you're going to use your kinematics equations. You're going to use the acceleration is due to gravity, which is equal to the mathematical value of 9.81. Really important to make sure you put negative on here because they're falling down. And so that's going to be a key habit to get into, that students tend to drop negative signs on this one, and it can really throw you off. The second thing is that for any of the other motion kind of stuff, when you're trying to figure out other parts, you can use those kinematics equations. So there they are. The only difference between the kinematics equations, as I put them in this blue box and the ones that you've seen before, is that I put the subscript y in there to kind of help emphasize that these only govern vertical motion to it. The other thing that's really key to kind of take it, or to keep an eye on, is what it says down here at the bottom. I know my camera is kind of, or my pictures are on top of it. Then we're talking about dy. Dy is this. It's the vertical height of what it is. And when you're talking about dy, it's a distance that's falling. You want to make sure that your dy is negative because it's going downhill. So again, if a is negative going downhill, then dy has got to be negative going downhill as well. And those are some key points that'll help you kind of move forward with this. All right, so between the two things, knowing that you've got horizontal motion and vertical motion, how do we put those two systems together? Again, the key here is time, that the object is going to hit the ground at the same time vertically as it does horizontally. I mean, it even sounds funny to say it that way. So if you solve for time, either horizontally or vertically, then you solve for time the other side of it. And they translate, I guess, between the two sides of it. So if you know t vertically, then you know t horizontally, or vice versa. So that's the key with all of these problems, is usually finding time and then using time to translate between the horizontal components and the vertical components. So let's take a look at a couple of problems here. We'll see how this works. I got a new little handwriting tool, so we'll see if this works on the screen for us. So we've got an example problem here. Projectile is launched horizontally off a cliff. It's got an initial velocity, 8.3 meters per second. The cliff is 125 meters tall. And how far away will the object land? So the first thing I'm going to do is I'm going to start thinking about sketching it. So I've got, my little cliff over here somewhere. I've got my cliff. Oh, see if I can make it actually drop. Hold on. This is definitely a different tool for me, so I'm trying to figure out how to make this thing work. My apologies. I want that one right there. Give me that tool. All right. So I've got my little cliff over here. I've got my rock up on top. It's going to be launched horizontally, so it's going to be going that direction, horizontal speed to it. But its path is going to be that sort of parabola kind of shape to it. Again, it's a little awkward for me to draw like this, but it'll work. What are some of the other things that we know? Well, we know that this side right here is 125. 1, 2, 5. And then we know that this side over here is 8.3 is the VI X. So in terms of doing that, and then the 125 is going to be D, hi cat, Y. So what are the pieces that we know? We're trying to figure out VIX. Do we have that piece yet? Well, yeah, VIX is given to us in the problem. We know that VIX for it is going to be 8.3 meters. Meters. Ooh, that's interesting. Meters per second. Meters/seconds. Okay, VIY. Okay, so this is one of the trick parts about doing this stuff. We're talking about the initial vertical velocity. So when we're talking about this rock, when it's falling off, and I'm just talking about this section of its motion going downwards, is vertical velocity when it starts is actually 0. It's not starting at anything. You're not like throwing it down off the cliff. You're not throwing it up off the cliff. You're literally throwing it horizontally. So as it's starting to fall, its original part that it's starting to go down, the vertical part of its velocity is 0. Again, that's a trick, but you got to kind of remember that vertically it's not really moving at all until you kind of let go of it. All right, so what else do we know? Acceleration, which is going to be in the y component because it's vertical, negative 9.81 meters per second squared. And again, that's going downwards only, so that's why we have the y component that's on here. dx. dx is the distance this way. How far is it going to fall? What's the range? And that's literally what we're trying to find. How far away there we go. How far away will it actually kind of fall in there? I'm going to get my pen back. Sorry. Awkward because I haven't just started doing this. How far away will it fall? That means we're trying to find dx. So that's our goal, is to find that. dy. Well, dy is vertical distance, and that's going to be the amount of vertical height that it's falling. And that's going to be, in this case, 125 meters. Now, why is it negative 125? Because, again, it's falling. And if our acceleration downward is negative, then our dy also has to be negative. And our time, we don't know what that is yet, but we can figure that out. Okay. So how do we start going about solving this? I'm going to kind of erase some of the stuff so I have some room to work. I'm going to get some of this stuff out of here. So what can we figure out to kind of use for this? Well, what do I have more information about? In this particular case, I've got some VIX, VIY. I've got A. I've got dx, which is what I'm trying to find. Since this is what I'm trying to find, dx, chances are really good that the way these problems are kind of worded, that I'm going to start with the y component since I'm trying to end with the x component. Again, it's just a trick in terms of how these are working. So I'm going to start kind of using some of this information. What can I figure out about the y component? So if I've got y component, I know that I've got vi. I know that one. I don't know what vf is. I do know what d is. dy is 125 negative. Again, because it's going down. And do I have any other pieces? I'm looking for time because that's always what you're going to end up be looking for. That's how these problems work. Oh, and I do know what A is, negative 9.81 meters per second squared. This is meters. This is meters per second. So do I have any information? Do I have a kinematics equation that would work with this? Well, yeah, actually I do. If I'm looking for time and I've got VI and A, usually the equation that you're going to end up working is the long one, df equals di plus vi delta t plus 1/2 a t squared. So with this, how do we answer this out? All right, dy, one of the things that's tricky for students is that df or di. Here's how I tend to like to think about it. I like to think about it the fact that at the end, it's going to be on the ground, and it's starting 125 meters up. It's kind of the way I think about it. VI, well, VI is 0. If I know that VI is 0, I know that this whole piece right here is going to be 0. This thing, VI delta t, is going to be 0. That's what helps us kind of solve this particular problem. And then I can use this part, 1/2 negative 9.81 times t squared. And now I just do a little bit of algebra. Negative 125 equals, I can't remember what that is. Let me get my calculator really quick. 9.81 times 0.5. I should know this by now. 4.9 equals negative 4.905 t squared. Again, 4.905 is 1/2 times negative 9.81. Okay, algebra. 125 divided by 4.905 is t squared equals 25.48 something or other and change. And that means that our square root of time, take the square root of our answer, sorry. Hold on. 20 square root of 25.48 is 5.047. So that means that t is 5.04, like 8 or so by the time I do it. So sig figs, we really only have like 2 sig figs in this whole problem. So I'll kind of round this now that I know it is. I know what my time is. My time here is going to be 5.0 seconds. If you want to do that as 5.05, that's fine. It really won't matter too much. So now I know how much time I've got to go to that. That tells me the answer of how long it's going to take for that thing to actually hit the ground. Okay, now what? That's always the next question, right? Let me erase some of this so I have some room to work. So my apologies. Okay, erase, erase. So now if I know what time is, and this is always the key, like I said, you're going to start with one side, you're going to use time, and then you're going to use the other side. In this case, we knew we needed to get dx, so we started with dy and started with the y component, used the y component to figure out what our time was, and now that we have time, now we can do some other stuff with that horizontal component. With the horizontal component, remember, this is constant velocity. Vx equals dx over t. Velocity is distance divided by time. The x component is always easier. We know what Vx is. The initial velocity is going to be the same as what was given in the problem, 8.3 meters per second. It's not going to change. Dx is what we're trying to find. Remember, how far away will the object land? So that's dx. And now we know what our time is, 5.0. So that means dx is going to be algebra 8.3 times 5, which the calculator says 8.3 times 5 is 41 dx, 41.5. By the time we do 2 sig figs, if you want to call it, 42 meters per second, meters is dx. Again, if you got 41 because it rounds down, that's fine, but that's that idea. Okay, again, key takeaways from this. Take a second, sketch your problem. Make sure you kind of know what's happening, that this little dude is falling off the cliff this way. You know some of those pieces like vi. You know some of those pieces like dy. And typically, whatever you're trying to find, like I'm trying to find dx, almost always in these problems, that means you're going to start attacking the other component first. So if dx is what I want to find as my last part, that means I'm going to start with the y component and do the math about the y component. If I'm trying to find something in the y component, then I'm going to start with the dx component. That's kind of how these work. All right, one more. I'm going to let you kind of try this one here. So what I'm going to suggest that you do, if you're watching at home, is that you pause this video at this point. You kind of read the problem, see if you can start picking away at it. Hit pause. Like I said, I'll work it out here in just a second, and then you can kind of give yourself a chance to sort of follow along. If you literally just sit there and watch, then that's fine, but it doesn't necessarily help a whole bunch. So like I said, this is example number 2. Give yourself a chance, draw yourself a picture, see if you can identify any of your little variables that's on there, and see if you can start kind of picking away at it. Okay, did you pause? Did you really? I think you're lying. All right, so here's what I'm going to do. Pitcher throws a baseball horizontally from the mound to the home plate. So what do we got here? We got a dude, right? Here he is. There we go. And he's throwing the ball. Okay. And then the ball falls about 1 meter. So he's throwing it this way, like that. And it's crossing home plate. Ball falls 0.926 meters. That tells me this distance, dy equals 0.926 meters. By the time it reaches home plate, 18.3 meters away. 18.3 meters is this direction, so dx equals 18.3. How fast was the pitcher's pitch? So when we're trying to find how fast, that means we're trying to find vi. We're trying to figure out how fast he's throwing it this way. And again, we're looking for it. This is going to be vi. In this case, it's the x component. That's what we're trying to determine. So what else? What other kind of information we know? Vix is our goal. That's what we're trying to find. VIY, again, projectile motions, if it's going horizontally, VIY is always going to be meters per second. It's acting like a free fall problem. It isn't going anywhere vertically at the moment that it's being thrown horizontally. Okay, AY, vertical component of acceleration, free fall, negative 9.81 meters per second squared. dx in this case is given to us in the problem. It's falling, it's going across to the home plate, 18.3 meters. dy is how far it's falling vertically, which is 0.926 meters. And time, again, we'll never have time, almost never. That's usually the thing that you're going to try to figure out. So again, step number one is going to be to figure this piece out and use it to translate between the x and the y component. So again, with this, we're trying to find Vix, which means I'm probably going to start by analyzing the y component. So what pieces of information do I have? Oops, don't know what that's trying to do. Interesting. We're trying to find some information about Vix. So if we're talking about we're trying to find Vx, so I got to talk about VIY. So that means I'm going to use information about this stuff, and this stuff. So what do I have? I've got VIY, I've got A, I've got dy. I'm trying to find time. Almost always that's what you're going to end up finding. What equation do I have that has Vi, A, D, and T in it? That's kind of the tricky question right now. So we know that this is 0. We don't know the final velocity. What do you think? What equation do we want to use? Do we have an equation that doesn't have Vf in it? Yep. It's going to be almost always the same one. Df equals di plus Vi delta t plus 1/2 AT squared. Same equation. So df, how far is it going? Well, it's starting at 0 and it's ending at 18.3. No, we're doing vertically. It's ending at 0.926, right? This is going to be, well, I should probably do this backwards. To me, it's falling, so I'm going to give that a negative sign to it. If I say it starts at 0 and falls 0.926, that works. Vi delta t. Well, Vi is pretty much always 0 in these things, so I know that one's going to be 0. Plus 1/2 AT squared. AT squared. What do we know about this particular thing? Well, we know what A is. So negative 0.926 equals 1/2 times negative 9.81 times t squared. Sorry, I kind of mangled that particular thing. So again, looks a little bit similar to the problem that we did last time. What did I say what this one is? Negative 0.4 whatever it was. Why can I never remember that? 9.81 divided by 2. 4.905. 4.905 t squared. 0.926. Now I'm just doing the algebra. Divided by 905 equals, see, calculator says, t squared equals 0.188, like 9 by the time you end up rounding it. And then I take the square root of that because this is t squared. Again, one of the other things that students tend to do is forget to take that square root. And this is 0.434 seconds. Again, 3 sig figs, so 0.434 seconds is time. So now, it's kind of nice I can do this, 0.434 seconds. By the way, if you ever get negative time, you've screwed up something. You've missed a negative sign somewhere. Go back and check. Can't have negative time. Did not go backwards in the universe. So that's kind of a weird process. All right. So now what? I'm going to get rid of this so I can have some space to mark here. Come on, go. I'm going to leave that message. All right, now we've got time. So now, if we've got time, that means we can switch over to the other thing, other side of it. If we were just solving for dy, now we can solve for dx or vx or whatever we're trying to do in the x component. And if we're trying to do vx equals dx over t. Remember, horizontally is the easy equation, no acceleration. We're trying to find vx anyway. We know how far it's going horizontally. We know it's going 18.3 meters horizontally, because that was what it says in the problem. And now we know what the time is, which is 0.434 seconds. And now it's just a matter of simple calculation to figure out what it is. So 18.3 divided by 0.434 is 42. Wow, that's kind of a good long ways. 42.1658. So 42.2 meters is going to be, meters per second is going to be the initial velocity in the x direction. So there you have it. Again, a couple of key takeaways about doing some of these projectile motion problems is that Trick number one, you're always going to be solving for time. You solve for time in one of the two dimensions and you use that in the other dimension. Keeping your x's and your y's straight is really, really important. Know that your x components, there's no acceleration. Know in your y components that there is acceleration due to gravity, and that your VIY, vertical velocity, is generally starting at 0 for horizontal launches. That's one of the tricks that students sometimes miss. If you're trying to look for an answer that's in the x direction, you're probably going to start mathing in the y direction. If you're looking for something in the y direction, you're probably going to start mathing in the x direction. So that's typically how these kind of work. So hopefully this gave you a little bit of review on how to do these sorts of horizontal projectile motion problems, and I'll post up a second one with projectiles launched at an angle. So after this, you should be able to go back and reattack that first section of the physics homework. I hope things are going well for you out there, okay? Hang in there, stay safe, spread love, not corona, right? See you guys soon.